Welcome back. So the first lecture was just about motivation for why we're interested in these kinds of questions. I'm largely motivated by the Langlands program. And today I'm actually going to get into some details and talk about the structure of Ewell-Horry algebras. And make the shift finally to characteristics. So let me set some notation first. So G for today is going to be SLN2B. So it's a bit of a change from last time, but it's going to make a few things a little bit more convenient. Most of the things I say hold for any kind of p-adic group. So I can take something like GLN, a symplectic group, an exceptional group, and I can take coefficients other than QP to get some finite extension. T would be a maximal torus. So all diagonal matrices. B is going to be a Borel subgroup, and I can factor this as T dot U, where T is the torus and U is the upper unipotent. So these are all matrices which are upper triangular. I is going to be my standard Ewell-Horry subgroup. So these are all integer matrices, which are upper triangular modulo P. So they look like ZP cross on the diagonal, ZP above the diagonal, and PZP below the diagonal. And again, when I write it like this, I'm always imposing the condition that the determinant is equal to 1. What else do I need? I'm going to take N to be the normalizer of G in T. So this is the normalizer. Of T. So these are what are known as monomial matrices. Let me not say much more about that because the thing that we're really going to care more about is this W, which is known as the Weil group. So this is N modulo T. And in this case, this is just isomorphic to Sn. And the way we think about it as a group is as the group of permutation matrices. Where I just have to impose this determinant 1 condition, so there might be some minus signs. Okay, so that's the basic notation. Oh, one more piece. I'm going to define Q to just be equal to P, just to make the things that I write kind of standard with what else appears in the literature. Okay. So this is kind of the group theoretic setup, and I want to give you first some group theoretic facts, which are kind of used as input into this whole story. And this follows from work of Baruch and Titz, and Ewell-Horry Matsumoto. Okay. So the main statement is that the pair I, comma, n is what is known as a Bn pair. So this is something kind of in the realm of group theory, and I won't give the full definition, but I'll kind of give some consequences of this. Okay, so more precisely, so again, if you want, you can look this up, and the keyword is Bn pair. But more precisely, what does this mean? So it means if I define W tilde to be this normalizer modulo T intersect pi, so if I define this, then this is what is called a Coxeter group. So this is just a group that has a particularly nice set of generators and relations with generators S tilde, and a length function L. So I'll describe all of this in this example once I'm done writing these facts. And this is what is known as an affine file. So you might have seen this W referred to as a Weil group, and it kind of comes with this particularly nice set of reflections called simple reflections. So for Sn, the simple ones are going to be just the transpositions that transpose adjacent numbers, so like 1, 2, 5, 6, something like that. There's a completely analogous structure here. So there's some set of simple reflections and a length function. And all this length function does, it's not too mysterious. This says that any element of W tilde can be written as some word in the generator's S tilde, and the length is just the minimal number of those words required to write that element. Okay, so that's the first thing. Second thing is the short exact sequence given by the following. So T mod T intersect I goes to N, T intersect I goes to N mod T goes to 1. Okay, so what are, so maybe I'll write it here. So this short exact sequence splits. And let me label what all of these are. So this thing is just what I defined above. This is W tilde. This is kind of the Weil group that I defined up there, so it's just isomorphic to symmetric group. And this is T modulo T intersect I. And T intersect I is going to be the same as T intersect K, so it's just all matrices which are diagonal and which have integer entries. So I'm just getting rid of all of the units on the diagonal. So a way I can think about this group is just the set of all diagonal matrices that have powers of p on the diagonal. Okay? And so this, it's not really going to be useful to us, but it's maybe helpful to think about. This is just isomorphic to z to the n minus 1. And it's n minus 1 because I have SLN. I have the determinant 1 condition. Okay, so this at least gives you, so the splits given W tilde is equal to W semi-direct product the intersect. Okay. So it at least gives you some way of thinking about this. Okay, this seems to have kind of. It at least gives you some way of thinking about this W tilde as a part coming from permutation matrices and a part coming from the torus. And the action here is just the natural action of permutation matrices on the diagonal matrices. Okay. What else can I tell you? So again, these are all kind of consequences of this Bn pair setup. I think this is actually what it's called a double Bn pair system, or double system. So we have a Bruja decomposition. So we saw this in the tutorial for the finite group SL2, but something completely analogous works here. So I can write G as the sum of I double cosets, and I'm going to put a dot here. So let me write this first. Well, okay, I'm going to keep writing W, but just keep in your mind that W is Sn. So I take a sum over the symmetric group, and I just pick an arbitrary lift of, this should be the affine Weil group. So I take an element here, and I pick a lift up to the group G, and I look at its double coset. So we saw in the finite case that, we could take as representatives this 1 and this kind of anti-diagonal matrix. here, I'm actually going to have infinitely many things. Right? Right. And what else can I tell you? Well, I can actually tell you a lot about these double cosets. So if I have two elements, W, W prime, and their length behaves appropriately, then when I multiply these double cosets, it kind of multiplies in the best way possible, like this. So in general, when I multiply two double cosets of any group, it's going to be a union of double cosets. But here it's saying I just get kind of the obvious one and nothing else. So the other property is if I have a generator, then I s dot I s dot I. So I can also tell you what this double coset is. And this will be, let me write it like this. It's kind of what you expect if you were to just multiply these. But I get something more. So I get something like this. So in these two specific situations, I can say exactly how I multiply double cosets. That's going to be relevant when we talk about product structures. And finally, I can actually tell you how big these double cosets are. So, I mean, this is a bit funny notation if you haven't seen it, but if I look at the index of I in this double coset, by which I mean just the size. So if I were to decompose this double coset into single cosets, I can ask how many of those there are. Well, this is just going to be Q to the length of W. So it tells me exactly how many double cosets, sorry, how many single I cosets I have in a double coset, and that's given by this length function. So again, I just kind of said this out loud, but I'll say it again. This length function L is the number of elements, the minimal number of elements of S tilde that it requires for me to write some W as a product of elements. So in particular, if I take my W to live in this set S, then I can just write it as S. So it takes one element, and it means that this index is exactly Q. So I'll go through an example next, but are there any questions on this section? Yeah, so T is just all diagonal entries, so you can think about all of these as being QP across. And then T intersects I, well, I think about diagonal matrices in here. So this is just going to look like a bunch of ZP crosses. So it comes down to understanding what QP cross, what CP cross is, and any element of QP cross I can write as a p-adic unit times some power of the uniformizer. So this is really just P to the Z. And that's where the Z comes from. And again, the reason that it's n-1 is because I have to impose this determinant 1 condition.
So, what is simple reflection?
I'm sorry?
In this case, what is the elements of H tilde?
I can't hear.
What are the elements of H tilde here in this case?
In S tilde? So I'll write those down. So yeah, let me go through an example and actually write down what these are. Okay. So again, if you've never seen Coxeter groups before, all of these things might seem very puzzling, but kind of standard in the theory of Coxeter groups. And you can do this for a more general kind of class of groups. So I can do this for a finite SLN as well. So for SLN over a finite field, where I replace this I by the Borel subgroup. And I get kind of an exactly analogous structure. I won't have something like this, but I'll have this double coset decomposition, and the B double cosets will actually behave in this way. So let me give an example to show you how this works. So W, in our case, was Sn, and I'm going to write these generators for this first. So this has generators S1, which is this permutation matrix. So it's kind of the off-diagonal thing in this upper corner, and ones along the diagonal. Like we saw, so this is just a bigger version of what we saw in the tutorial. S2, completely analogous. It's like this. And I go down to Sn minus 1. It's here. This. So W is a finite group, right? It's the symmetric group. And it's generated by these n-1 elements. Okay? These are transpositions of adjacent numbers. Okay? And on the other hand, W tilde, so again, let me write it. So then T intersect I, W semi-direct product T intersect I. So it contains W, so it's going to contain these. And this has generators, which are given by the following. So I'm going to take all of these matrices, so S1, S2, Sn minus 1, and I'm going to add an extra one. So S0 is as follows. So I'm going to put a P in the bottom left corner. I'm going to put a minus P inverse in the top right, and then just ones everywhere else. So if I was thinking about this element as an element in Sn, well, then I could kind of absorb the P and the P inverse into the torus part. But since I'm only modding out by integral things, this is a distinct element. Okay? And so this is my set S tilde. And the claim is that if you give me any element in here, W tilde, I can write it as a product of these, some finite quantity. There are some relations among these generators, but I'll kind of come back to those. Right, and maybe let's note that each Si, if I square it, I get 1. So this is another property of this generating set S tilde. We want them to be reflections, so we want them to have order too. If I kind of square these ones are maybe easier to see. For example, if I square S1, I'll just get minus 1, and then 1's everywhere else. But minus 1 lives inside of T intersect I, so it's the same as the other. So for SLN, we can be extremely explicit about what these generators actually are. And again, the length function is just the minimal number of these that are required to write some element of W as the problem. Yeah. here? This one? Yeah, let me rewrite that. So this is minus P inverse. Okay, so questions here.
Why did you use the generators as -1? Like if you were choosing 1 in place of minus, like place -1, those would have still been generated.
Why is this what you're asking?
Yes, yes.
Because I want it to be an SL.
Oh,
Yeah, I want it to have determinant 1. I mean, it doesn't really matter where I put the -1. If I put the -1 here instead, then they're going to be the same in this file group because I can modify it by an element. This is just a particularly nice thing.
Just this one extra generator is not makes it an infinite group.
So what is the question?
You just have the generators up to Sm minus 1 and get Sn.
Yes.
Just that one extra generator makes it an infinite group.
Exactly. Yeah. And that's usually what happens. There's some finite portion, and then this kind of infinite portion I get by adjoining usually one extra element. Depends on something about the root system. Okay. So let me recall this Hecke algebra from last lecture. So you've seen it a bunch of times already. And for now, I'll still stick with C, but we'll see that in about 2 minutes that this is really not necessary. And then at some point, I will switch to FP1. So again, F has compact support, and F IGI prime, F of G. For every I prime I. So this is what we defined last time. We've seen it in a few lectures already. Let me tell you what the product is on this thing. Or actually, before I do that. Oh, this is excellent, actually. So I have this. I have the space of compactly supported functions that are I bi-invariant, or if you like, these are finitely supported on the double cosets. So the Bruja decomposition gives, how do I say this? That basis for this Hecke algebra is given by these things that I'm going to call TW, which I define to be just a characteristic function of I W dot I, where W ranges over this affine bound. So, for example, for any of these generators, I can look at its double coset, and that gives me the basis element as a C vector space. Okay, so this is part of the group theoretic facts that I'm using. The Bruja decomposition gives me the basis. So this is already some things. And now I will finally tell you what the product structure is. So the product structure on HGI. So I mentioned this before. This is given by convolution. And so if I take two functions here, then I define their product G, and let me kind of for the last time use that I'm working over the complex numbers. If you've ever taken a course in functional analysis or something, then know that convolution is given by some integral. So I take the integral over g. Make sure I get this right. This is f of h, f prime, h inverse g. d mu g. So this is what convolution looks like. And here, maybe I'll just point out that I'm taking mu to be the Haar measure, which gives this Iwahori measure 1. So if you haven't seen this, it's not really going to be important for anything I say, but this kind of convolution comes up very often in functional analysis, and this is kind of the formula that one uses. You've seen it, of course, in Fourier. Oh yeah, but yeah, the point is that I take this Haar measure to give the Iwahori subgroup measure 1. But now here comes the kind of nice thing, and this is the general fact about locally constant functions on p-adic groups. They're much nicer than locally analytic, just the R functions. Locally constant functions, anytime I have an integral, I mean, this is kind of a fancy way of writing something actually quite simple. This is going to decompose as a sum over h in g mod I of f of h, f prime, h inverse g. So even though I kind of wrote this fancy integral to maybe relate it back to some things you might know as convolution, it really just becomes a sum. Okay? The fact that I can write it as a sum comes from the bi-invariance of these functions. And, well, I mean, this is an infinite set, but this is actually going to be a finite sum because these functions have to be compactly supported. So there's only finitely many non-zero terms in this thing. So there's like no issues of convergence, right? So now I've given you the algebra, I've given you a basis, and I've given you the product. And now here's the kind of the big thing to note, is that the definition of HGI and the product kind of in this form makes sense for any ring R instead of C. So for example, take this R, the F equal. Okay. So even though I define this as an integral, kind of some complex thing, like right from the beginning, I could have taken functions into F p bar and used this as my product. There's another, I guess, kind of point of origin of this product that I'll discuss in a little bit, but yeah. So the first lecture again was over C to be motivational, but this structure kind of works exactly the same way over any ring, and that's because I'm not taking fractions anywhere. Everything is working over the integers. So I guess I've kind of done my goal and define the Heck algebra for you and define the product. But now I'll kind of go on and tell you more properties of how this thing behaves. But before I do that, are there any questions? Okay. I realize I might be going a little fast, and that's because I think I have more pages in my notes than I have time. So I'm going to do my best to kind of get everything.
So we see this algebra as a module over some ring?
In what way?
As a module over some lecture like KG module or something?
Well, you need to put a product on that thing. So I'm not sure. I mean, we can think about this as the endomorphisms of some compact reduction. That's another way to do it.
What is the relation between S0 and SI?
Sorry?
What is the relation between SI and S0?
What is the difference?
What is the relation?
Relation.
Yeah, I'll describe some of them in an example. There's actually a very nice way of kind of seeing all the relations from something called the affine-Vinken diagram, but if you haven't heard those words before, that's fine. I'll write these down in examples. The Haar measure on G is unique if you normalize it this way.
It's not linear.
Sorry?
It's not a linear.
It's still what is called unimodular. So there's a unique Haar measure of the scale. The problem is that a Haar measure won't make sense if my ring is this. I can sometimes define Haar measure when I have, say FL coefficients, but I can never define a Haar measure when I have FP coefficients. So that's why I use kind of this definition.
So can we study this Hecke algebra when R is ZP or something?
Yeah, so you can define it for ZP.
Do we get something more than what we get for, let's say,
Well,
fields?
you don't get anything more, but you get some sort of interpolation. So
Okay.
if you define it over ZP, then you can invert P, and you have like a characteristic zero Hecke algebra, which behaves like the complex one. But then you can also reduce mod P. So for example, if you have like a module over the ZP Hecke algebra, you can both kind of think about it as a characteristic zero thing and a characteristic two. Other questions? Okay, so so technically I've told you what the product is, but let me try to answer the following question. What is the product in terms of this basis TW? So I gave you a basis that's kind of very convenient, and I want to know what the product is in terms of this basis TW. And so I won't tell you kind of completely, but I will tell you kind of the kind of enough so that you can figure out the product. So here's the theorem, again due to Mori Matsumoto. So first, if W and W prime satisfy L of W, W prime, so if they behave the correct way with respect to length, then T of W, T of W prime is T of W. So maybe I won't write kind of convolution anymore. I won't write star in between these. So if the length on the affine vowel group behaves correctly, then the length is going to behave correctly here. And the second relation is if S is a generator. And so maybe by the way, to give a silly example of this, if we go back to the tutorial, what we were multiplying was, when we were doing all those convolutions, was T1, which is the identity, and TS1. So if I multiply those, the length on those behaves correctly, and so I can just multiply them in the group and just get what I need. And now on the other hand, this was the calculation of B2, B2. 2. So if S is in S tilde, then TS squared is equal to Q minus 1 TS plus Q T1. This is exactly what we saw in the tutorial, and the proof is, I'll say, essentially the same as the calculation. It obviously requires a little bit more work because now we're dealing with infinite groups, and we have to think about various coset decompositions in these p-adic groups, but the moral is the same. So again, I always have 1 in W, and T1 is just the characteristic function of the Ewald-Hori, and that acts as my identity. This is the identity element. And again, I've kind of written this in C, but this relation works over any ring. And I'm not inverting any integers, so this holds whether I work over C or whether I work over FP. If I work over FP, well, this Q, remember, was just equal to P, so this is going to go away and this is going to go away. So in characteristic P, the relations are a little bit simpler, but this presentation works over any ring. Maybe I should say, these are often called the Bray relations. These are called the quadratic relations. Sorry?
First one followed immediately from that. You raised IW,
Yeah, exactly. So these two group theoretic facts are kind of manifested in these. So what one shows, if one plays around with this convolution product, is that this product has support contained in the product of the two double cosets. So if the length behaves correctly, then the product of the two is just a single double coset, and all you have to figure out is, so that means the product just from that fact is some scalar multiple of this, and then one just has to figure out the coefficients. Same thing here. When I took ISI, then that was ISI disjoint union I. So I know that this result is going to be some linear combination of TS and T1. And figuring out those coefficients is kind of where the work is. So there's some input from this kind of BN pair business, but it really kind of simplifies these things a lot. Okay. So let me do some examples. Just to kind of make this a little more precise. So I'm going to do SL2 in this, and basically just kind of recap what happens. So W tilde is generated by S1 and S0, which means that any W and W tilde can be written as S1, S0, S1, S0, or S0, S1, S0, S1, some finitely many times. These are going to alternate because if I ever had like S1, S1, well, I know those multiply to give me 1. So I can always kind of concatenate those. So as long as these things alternate, this will be what I've been calling minimal length expressions. And so in this case, this length function is not anything mysterious. It's just the length of these. And the consequence this has, if I kind of unravel it, is that TW can be written as TS1, TS0, TS1, TS0, however many times I need to, or kind of the other. So the Hecke algebra is infinite dimensional, and this is its basis, but again, this is a basis as a vector space. What this shows is that if you give me a TW, I can always write it as a product of TS0s and TS1s. So what this means is that HGI is generated by TS1 and TS0. This is as an algebra. So if I take products of these two, it gives me everything. Subject to the relations, well, this writing it this way is essentially a consequence of the braid relations, being able to kind of pull things apart. And the only relations I have to impose are the quadratic relations. So if you've ever done kind of a very abstract version of algebra, any kind of C algebra, I can always present in terms of generators and relations. And this actually allows me to write down a presentation for this algebra. So it's, if you want a non-commutative polynomial algebra, then these two generators subject to these two relations. And this is actually enough to tell you quite a bit. So just from this, you can write down something like the center of this algebra. Okay? This algebra is not commutative because TS1, TS0 is not the same as TS0, TS1. And that's because the group W is not commutative. Okay? So you can ask about things like the center of this algebra, and that's a fun exercise to think about.
So, first an easy question, where's the word braid relation coming from?
I think I'll explain that next.
The second thing is this exactly the non-commutative algebra that came up in what is T1, 2, and T-1, 0? Because it looks like the definition is the same except for SL2 and GL2.
Yes. So I will say it is possible to write this Hecke algebra in terms of your generators, but I can never remember how to do it. Like if one sits out, it's possible to be worked out. But somehow this is the one I can remember. The other presentation is a little bit more difficult. Other questions? Okay, so maybe to answer.
Yeah, I mean, this is from Baruch on my lecture, from Baruch generators and relations. Like the second relation doesn't look like something familiar in that word. If you go mod P, what is that?
If you go mod P, it just looks like TSI squared equals minus TSI.
So for example, if we square T10, we get derivative.
So
we don't get this exactly.
yeah, maybe one small comment is that I'm working with SL2,
Yes.
and that does affect things a little bit. I'll do the GL2 example in just a second. So I think I have two more examples which might answer both of those questions.
Maybe so T10 is given by beta, which is not a coset here, but T12 might survive. And if you look at T12, T10, T12, that's minus T12, right? So if T10 is not present, that's the first relation, is it?
Yeah, it's very analogous.
So it turned away from
So T12, T10, T12 is minus T12. suppose T10 is dropped from that, then it says T12 square is minus T12, which is what you get. T12 is not there, yeah.
I is 0 and 1. Yeah.
Sorry?
I is
Oh,
0.
yes, yes, yes.
That's the nearest thing.
Okay, maybe I can continue and we can, maybe what I'll say will
You're
clarify.
raising some interesting questions.
Yeah. Right, so this group W in this case is just generated by these two, and there's very few relations, right? So the only relations are that both of S1 and S0 square to 1. Note, if G is bigger, there are more relations in W tilde. So, for example, if I go up to SL3, then we have an S1, S2, and an S0. So in W tilde, we have the following. So essentially, in this SL2 case, there are kind of no relations other than these square relations. But for SL3, we have the following thing. So S1, S2, S1 is S2, S1, S2. So this is something you can check. And this is why it's called the braid relation. Because if you think about permutations of Sn as kind of imagine n dots on top, n dots on bottom, and a permutation as being strands, then if you write down pictorially what these strands are, you get a bunch of crossings. And if you braid them together just by moving the strands around, you can do it this way. This is a fun kind of pictorial exercise. But this is called the braid relation in the affine Baruch. And what this leads to, if I use those relations, I get that TS1, TS2, TS1. Well, this is TS1, S2, S1, which in the file group is S2, S1, S2, which is TS2, TS1, TS2. So in addition to quadratic relations, I have things like this, which mirror exactly what happens on the level of the file group. And I guess that's where the name braid relations comes from. So questions about this example? Sorry? Okay. So this I decompose using that first relation, and then this element is yeah, this is a sideways equality sign. This is an equal sign turned 90 degrees.
The first line.
Yeah,
So
this
that's
is
a
once you
great
go around.
relation at the top. This one is close to this one. We have to check that.
Questions? Okay, let me do one more example. Where G is GL2. So I kind of said at the beginning that I want to take SLN to keep things a little bit simpler. And the thing I want to use about that is that the group is semi-simple and simply connected, which is not the case here. So one can work out the analogous theory for GL2QP, but there's kind of extra details one has to worry about. So let me kind of just indicate what happens here. So in this case, W, which I can define in the same way, is almost epoxy group. And the key word is almost. So you're not going to get this kind of presentation on the nose. So what you see is that W tilde is generated by S1, which is the same, S0, which is the same, so I'll just keep these the same, and an extra element, which I'm going to call omega, which looks like 1p. And you can still put like a length function on this W, but what ends up happening is that this element has length 0. So it gives you some non-trivial element of this affine vowel group, or what's called an extended affine vowel group, that has length 0, which is maybe a little bit weird to think about. But this is essentially equivalent to this element normalizing the Iwahori sum. So this showed up in a few of the talks. We have this extra element in GL2 that normalizes the Iwahori, or stabilizes the edge in the Bruhat tensor. And that's exactly analogous to this length position. Okay. So the effect that this has is that the Hecke algebra, in this case, so I'll kind of skip the details, is generated by TS0, TS1, and T omega. So now I have these 3 generators with some extra relations. So I'll write down some of the extra relations. So I still have the quadratic relations. So maybe in addition to quadratic grade. So I also have the following. So if I take T omega squared, well, because it's length 0, then this kind of grade relation, a generalized version, still behaves correctly. It becomes T omega squared, which is T dp, and this is central. So I get an extra central element. And I can do something like this. So it so happens that T omega is invertible in this algebra. The TSIs will not be invertible. For example, if I'm in characteristic P, generally it won't be invertible, but T omega will be. And here, I get this kind of relation. And analogously, I have this relation. So if I kind of use these kinds of relations, then it's possible to get to kind of these T10, T-10. But again, I don't.
So it looks like TW is T10, and it looks like TS1 and T0 are T12 and T-10. What are the two? Because you conjugate either of them by TW or by
Exactly. So
T10,
one can work this out.
You get the other one. So
Precisely.
what about those are the relation with the negative sign many times out? It was in the tutorial also.
Right. Well, I think towards the end of the tutorial, they wrote down this idempotent. And the idempotent will essentially be, I think, minus TS1. If I take...
Maybe that's coming from this, that relation?
Yeah, this is essentially an idempotent relation. Except it has the wrong sign, but if I take negative TS1, I'll get exactly. So this is the presentation that I can remember. The other one is and maybe I should say, just to kind of finish this up, for SL2, somehow I needed every generator of the file group to generate the algebra. Here, I said, kind of from general facts, that HGI is generated by these three. But this shows that it actually suffices to take T omega and TS1. Because once I have those, then I can get TS2. So in fact, I can get a smaller generating set. So if I'm ever looking to calculate the action of HGI on some space, for GL2, it suffices just to work with these two. This action is often relatively straightforward. Okay. All right, so are there any questions here? So maybe the takeaway from this should be that this really is quite an explicit presentation of this algebra. Maybe if the group is a little bit bigger, I have a few more relations to worry about, but one can actually work with these things and even write down things like the center. So now let me kind of move on to modules of this Hecke algebra. So let's suppose V is a G representation. So I'm back in the setting where my G is SLN QG. So then I mentioned last time that EI has the structure of really, if I'm doing this, it's a right HGI module. Okay. And let me write down what this is. So if take a V in VI and a W in W tilde, well, let me write it up there so it's more visible. Then V, TW acting on the right on V is given by the following equation. I take a sum over H's in I mod I intersects W dot I W dot inverse H W dot acting on. So this is the group action that comes from the G representation. And then this is just what the action is. And I'll mention in a moment kind of where this comes from. And the point is that this lands, this action lands you back in the I invariance. So the first lecture I didn't really mention this. I just said that if you have a representation and a vector in here, then this thing has an action of HGI, and here it is. So let me give an example to show you that this can really be made explicit. And I think this is going to be worked out a little bit more precisely in the tutorial section. So again, SL2. And again, I sort of prefer working with SL2 over GL2 because the formulas end up being a bit clearer. There's fewer parameters to it. So I'm going to let G be SL2, and I'm going to let B, just to keep it simple, be the parabolic induction. Oh, sorry. Hold on. Be the parabolic induction of the trivial character. The trivial character on T. So we've seen parabolic induction many times before, so let me not go into too many details. Again, these are all functions on G that transformed by this character when I act by b on the left. So since I have b here, it just means all functions on g mod b. So then, one can compute that bi is the span of two functions. So this is finite dimensional. FBI and FB S1I. Where the support of FBI is BI and the support of BS1I is BS1I. And this should tell you everything you need to determine what these functions are. So it's a good exercise to actually think about why this is the case. And yeah, maybe that's an exercise to do. And what is helpful here is to use the Iwasawa. So the fact that this element has length 0 is the same, is equivalent to it normalizing the Iwahori. So if I conjugate the Iwahori subgroup by this element, I just get the Iwahori subgroup. Okay, so I have these two. And using this formula, I can actually calculate the action. So using the formula, I can calculate. I mean, and these are all like quite explicit objects. But what we can do, maybe let me not write down the whole answer. I should leave something for the tutorial session. But to figure out what this thing is as a module over this Hecke algebra, I just need to tell you what the generators do. I don't have to tell you what every TW does. All I have to figure out is what TS1 and TS0. So for example, if I take FBI and act on it by TS1, well, again, what do we know? This is going to be another element of BI. So it's going to be a linear combination of these two. So it's going to be, so I just need to figure out those coefficients. And what I get is that this is the S1I. That's not too bad. And if I take this and look at the other generator, again, this is going to be some linear combination. And in this case, I get Q minus 1 FBI plus Q. And then maybe in the tutorial, we can discuss how to do what is the definition of FB? So it's the unique function in here, which has supports BI and is fixed by I. So, I mean, if what you can do is you can take it to be the characteristic function. So this is like a worthwhile example to work through, just to really give you the idea that this is something quite explicit. And because I want to kind of ease the transition into characteristic P, notice that this calculation also works for characteristic P the same way it works for characteristic 0. Except in the end, you'll get that these Q's go over. So if I did this from the beginning with characteristic P coefficients, the calculation would be the same. So this is quite explicit. And yeah, maybe a good exercise also is to work this out for the supersingular representations. So there, you also have quite an explicit presentation of the supersingular representations for GL2QP. And fortunately, Broy calculated this for you in the I1. So you can do an analogous calculation where you figure out exactly what this is as a hegemon.
Function is the sum of those two functions.
Yes. Yeah, so in particular, this is reducible, but that doesn't really affect the calculation. Okay. So I'm doing okay on time. So I want to make a quick remark. Where do the formulas for, let's say, the product for the action on VI come from? So you have no reason to believe that this is like a good formula. Right? I mean, I've just written down something for you. It's maybe not even evident that when I take this sum, it lands back in the VI. So I should try to justify why, like, this is the action and why it gives you an algebra action. And the short answer is that this comes from Frobenius reciprocity. And we've seen this a few times before, but let me take 2 or 3 minutes just to remind you of how this works, in case you actually want to kind of rederive these formulas yourself. So let's say if B is a representation of I. Oh, sorry, the other way. Oh, that's a. Say if U is a representation of I, and V is a representation of G. So then we know that the I homomorphisms from U into the restriction is the same as the G homomorphisms from the compact induction from I to G from U to B. And moreover, one can make this explicit. So if I have a homomorphism here, I map it to a homomorphism here, where F evaluated on GV is just G acting on F. So this is, this is more than just like an abstract thing. You can make it really explicit. So you can say exactly where this goes. Oh, I shouldn't use V. I should probably use U. So that's one thing. And the other thing is, I think this was maybe mentioned in passing, but if I have homomorphisms from the trivial I representation, into I. Well, this is going to be the same as the I invariance. How does that go? Well, so if I have a homomorphism F, I just send it to, B is also that. We call it alpha. So alpha is just a fixed basis vector. Of this trivial representation. So 1I is the notation I'm using for the trivial representation. It's one-dimensional, so I just pick a basis vector. And if I go here, well, if I imagine acting on I on F alpha, since F is I equivariant, I can slide this inside, and I acts trivially on alpha. So both of these isomorphisms you can make extremely explicit. And so here's the diagram. So I have VI, and I have HGI acting on the right. So I get a map like this. But this VI, we said, was Hom I from the trivial representation to V. So this is the action map. So that's that map. And HGI, so remember this is bi-invariant functions. So I can think of it as I equivariant homomorphisms from the trivial representation to the compact induction of the trivial representation. So these are functions which are invariant on one side, and by taking I1 invariance, I get invariance on the other side. And so just to save space, I'm going to call this X.
It's restricted to Y.
I'm sorry?
Compact induction, one restricted to Y.
Sorry.
This is
Yes.
representation of Z.
Right. And now I use Frobenius reciprocity. So this is Hom, G equivariant Homs from this X, because I have compact induction, to V. And this is G equivariant Homs. Well, I put a compact induction on this side, X to X. And this goes to, if I use Frobenius reciprocity all the way here, G equivariant Homs from X to V. And when I kind of look at the bottom line, well, there's only kind of one reasonable thing I can put there. That's just composition. So this arrow is composition. What is X? X is this compact induction from I to G. Just so I don't have to write compact induction. So if I have a homomorphism from X to V and a homomorphism from X to X, I can just put them together to get another homomorphism from X to X to V. And that's what I get. So this is, I would argue, the more kind of natural way. And then if I just translate it through, it gives me kind of an action on these spaces. There's several isomorphisms one has to unravel, which is, a good exercise. So this is how I get the action. And so I've erased the product formula, but one can do the exact same thing for the product formula. So if I put HGI here, and have it go into HGI, then I can do the exact same thing. Here I have composition, and going up here will give me the product on the Heck algebra. And again, this is a viewpoint that doesn't use the fact that I'm over C at all. It works over any. Sorry? Second or this one? Here? What about it? Yeah, so this is a one-dimensional vector space. Let's say alpha is a basis vector. So to figure out what this homomorphism does, I just have to evaluate f on alpha. So that gives me a vector in V. Okay? But what extra properties does it have? Well, if I try to act like I, then since it's I equivariant, I can put I inside, and I acts trivially on alpha. So this vector, in fact, lands in V. Okay. So further questions? This one? This one? This? So this is this action that I wrote down. Okay? So what I'm claiming is that if you start with this bottom line, which again is the kind of natural thing you would do, and trace it through these isomorphisms, then what you end up getting is exactly this formula. So this is a checklist. But that's kind of justifying that this formula is not coming out of thin air. It's actually coming out of something much more natural. Okay. Right. So yeah, now kind of comes the big switch. So I'll just repeat. So everything we've done so far meaning the structure of the Hecke algebra, this action that I just erased, the basis, all works for any ring I want. Okay? And that's because I didn't have any denominators anywhere. So I can really just plug in any ring instead of C. So in particular, it works over any ring. So what we're going to do is, so my coefficients, I'm finally going to take to the FP bar from now on. Okay. So what that means is that everything I've said today works over FP bar, except the Q's go away. And now I'm going to focus on kind of extra features that occur in this set. But I need to make one small tweak. So in fact, so we know that in characteristic P, it's sometimes better for various reasons to work with pro-P groups. And I is not pro-P. So maybe not easier, but better to work with I1 instead of I, which is what is called the pro-P Iwahori set. And what does this look like? It almost looks like the Iwahori, except I'm going to put 1 plus PZP on the diagonal. So these are matrices which are upper triangular and unipotent modulo P. And this happens to be, so there's a notion of CELO subgroups, even in this infinite setting. And this is the unique pro-P CELO of I. So, and the difference is, so this subgroup is normal in I. And the quotient, since the only thing I'm changing is the diagonal, the quotient is going to be some diagonal matrices which have order prime to T. So it's not too far off from I. So let me tell you a little bit about what's going to happen. So also, we're going to let H denote well, the same thing as we had before, except with I1. So this is the pro-p-Iwahori Hecke algebra with coefficients in FP. So this is going to be our focus from now on. This is the pro-p-Iwahori Hecke algebra. This also makes sense over C, but again, our focus is going to be FP over FP. And I don't want to go through this whole kind of structure theory again, because it gets a little bit more technical. There's more things I have to worry about. It's not exactly a Coxeter group structure. But I'll just say that much of the structure of HGI works similarly. So let me, instead of writing down kind of the generators and relations thing, let me give you kind of an example of what I mean, that much of the structure is the same. So maybe, for example, a basis for this space, so I'm switching notation, I hope that's okay, is TW. And again, in a similar fashion, these are going to be I1 double cosets. This is I1 W tilde I1, where W is in W1 tilde, and now I need to tell you what W1 tilde is. So W1 tilde is going to be this same normalizer, but now I mod out by something a little bit smaller. So instead of T intersect I, I'm going to take T intersect I1. So this is the difference. I'm taking T intersect I1. So this is a little bit bigger than the W I had before. What do I want to say about this? This is, and I'll say, this is kind of very close to W. So just to kind of say quickly, there's a surjection from W1 tilde onto W, just by making this group a little bit bigger. And the kernel of that surjection is just a finite torus. So it's the kind of a torus part that comes from the finite. So this W1 tilde is not super mysterious. It's very, very closely related to this.
That's not exactly split for that also?
That one is not split. Yeah. So I have a surjection from W1 tilde onto W tilde. The kernel is some finite group, order prime to p, but that one does not split. So I can write down a basis for it. I can also write down grade and quadratic relations. So the TW satisfy grade and quadratic relations. So let me give you an example of one of those. So in SL2, so like I said, it gets a little more technical. So if I take TS1 squared, well, so what I get is again going to be TS1 plus something. So what I would expect from like the Iwahori case is the identity here. I don't quite get that. I have the double coset of this element, okay, which doesn't appear in the Iwahori case because this element is already contained inside of I. But it's not contained inside of I1. Also, let's assume P is not 2. I really don't like the primes. So I do get a Q here. And here, again, I would expect like a Q minus 1. So I don't exactly get that. Instead, I get a sum over X in FP star of these elements. So again, I really should be taking lifts, but this is what I get. And so, for example, if you imagine that I do some sort of projection down to W tilde, then this would go to 1, so I'd get a T1 here. And each of these would go to 1, because these are all contained in R. So I would get Q minus 1 of these. Remember, Q is equal to B. And so if I kind of project everything, then I get exactly the quadratic relations I had before. But in this case, I have to be, a little bit more precise. But so this is what the quadratic relations look like. Yeah, a little more complicated, but still, like, if you're willing to sit and work with them, they're not so bad. And again, in characteristic P, this part is going to go. Okay. And maybe the final thing is, so even though it's a little more complicated, yeah. I'm sorry? S0 satisfies the same relation. For SL3, I would have to be a little bit more careful. I would have to it's analogous relations for the other simple relations. And so we have a complete classification of simple modules, description of the center, etc. So let me name some names. The study of this algebra, kind of in wide generality, sort of wider than just SLN. It's kind of initiated by Vigneros. There's some work of Olivier and Abe. So even though it's a little more complicated, it's still not too far off from this case, where we have an incredible amount of control over the structure. Okay. And now, okay. So I'm almost at time. I think I can finish if I have 5 more minutes. So let me indicate why this is the right thing to consider. Okay? Characteristic. Why is H a good object? Consider characteristic. Well, we have this P groups lemma, which says maybe the Prof P groups lemma, which says that if V is non-zero, so this is a G representation, then VI1 is non-zero. So this is already like a different situation than in the complex case. For example, if you know what a supercuspidal representation is in the complex setting, supercuspidals never satisfy this condition in characteristics here. But any representation that's non-zero does satisfy this equation. So somehow this even captures supercuspidal representations. And here, again, I have an action of this mod P pro P Iwahori Hecke algebra. So the kind of the upshot is that VI1 sort of carries more information. so somehow this P group's lemma tells us that this I1 is really something that we want to work with. Because well, we can try to understand representations through their associated Peckermodule. Okay, perfect. And let me just kind of point out the way in which this information goes. This is a theorem. Rasha, Olivier, myself, which says, let's suppose that G is GL2QP or SL2QP. So then, the following category. So this is very similar to what I wrote last time. So these are the representations of G that are generated by their I1 invariant vectors. So these are the V and rep F PG, such that if I look at the G representation generated by the I1 vectors, I get G. Well, I can produce an H module out of this by taking a V and going to VI1, okay? Just like we did in this procedure here. If I have a non-zero thing, I get a non-zero thing. And this is an equivalence of categories. So this is kind of the mod P analog of this theorem of Borel and Bernstein that I wrote down last time. There are slight differences. This is not a block anymore. So again, if you don't know what a block is, don't worry about that so much. But you should think about this as the analog of the theorem of Borel and Bernstein. So I have this kind of subcategory, and it's equivalent to the category of H modules. So I can understand representations using Peckermodule. So let me just mention two things. So one is another difference of the FP case and the complex case. So in particular, so the difference is, if I look at this category with complex coefficients, this doesn't contain supercuspidal representations. So again, these are the supercuspidals are in some sense the building blocks. So this has no supercuspidals. But well, I know that any irreducible has non-zero I1 invariant vectors. So if I look at the G representation generated by that, that is going to give me everything. So in particular, the left-hand side contains all irreducibles. So really, it's really all irreducible representations. So what we get is analogous to the bijection that we had before, that if I take an irreducible G representation, okay, again, for these two groups, these are in bijection with simple H modules. And maybe you can believe me that it's not so bad to write down the simple Hecke modules in these cases. For SL2QP, in the Iwahori case, I gave you like a very explicit presentation. And actually from that, you can find the simple modules fairly, I don't want to say it's easy, but if you sat down at it for a little while, you could probably start to write down some simple modules. So in these two cases, we can really think about irreducible G representations as simple modules, including the super singular ones. Because the super cuspidal ones I can think of in terms of their Hecke modules. But let me just end on kind of a sad note. So I've told you all this cool stuff, but let me tell you about the sad thing. So this is let me call it here. Due to Olivier, is that this equivalence fails for GL2 UP to the F, where F is greater than or equal to. So this is the unramified extension of QP of degree F. So similar to Professor Gatte's course, even for a QP squared, for that quadratic unramified extension, this equivalence is known to fail. So the theorem of Berlin-Bernstein that I talked about over C kind of works for any group and any field extension. But this theorem is quite specific to these two specific groups. If you try to change the field or change the group to something like SL3, it's also known to fail. So things are not quite as good in the characteristic P case from that point of view, but at least for SL2QP and GL2QP, we can get a lot of information from this kind of viewpoint. And so in the next lecture, I'll try to discuss some applications of how we use these Iwahori technologies. Okay, so I'll stop there. Sorry for going over.